So, yeah, so this talk is going to be about gradient flow or general flows in high dimension and asymptotics and some universality. Is mainly based on a paper with Michael Celentano and Chen is here. That hopefully we will post online this week or next week. And if time permits, I'll mention the result with Basil said. More preliminary, so. And perhaps the starting point is for those of you that were yesterday at Freddie's talk. It should be clear that we have a lot of tools. So this is going to be a talk about tools, and it's quite clear that we have a lot of tools to deal with the problems in which we do empirical risk minimization, possibly in high dimension, when the loss is convex and the data are Gaussian. For instance, Gaussian comparison inequalities are a very powerful tool to deal with that. Now, of course, this has some limitations. First of all, we know that often data are not Gaussian, either because they are not Gaussian to start with, or because we process them through a few layers of a neural network. Secondly, we know that often we are interested in non-convex objective, especially in deep learning. And third, we know that in the over-parameterized setting, we don't have a single empirical risk minimizer, but we have many empirical risk minimizers. And so what we're really interested in is the empirical risk minimizer to which gradient flow converges. Right now, in some cases, we can characterize that like the mean norm interpolator, but in general, we don't know what is the implicit bias. So this is an attempt instead to forget about this and analyze directly in some simple models gradient descent or gradient flow, and let me give you two examples that are covered by the kind of results that I'll discuss. The first one is generalized linear models, high-dimensional generalized linear models, but unlike in classical statistics, I look at non-convex models. Okay, and what do I have in mind? I have in mind that I have data, responses and feature vectors, and perhaps these data are some function of noise variables. And then the way we fit this data is we try to minimize over some vector theta in RD, some loss function that is, okay, I'll use this scaling because this is paper. Plus perhaps some regularizer. Okay, and what I'm interested here in understanding is, for instance, because this is L0 gradient flow. That is. And this, of course, takes the form, if you write down the derivative, this takes this form. Okay, there is the memory term, the regularization term. Where here L0 prime is the first derivative of L0, the derivative with respect to the first argument. And okay, of course, there is a factor that I forgot in my normalization, and this is applied component-wise. Right, so this is one example we might want to analyze. And In this case, we might want to know to which empirical risk minimizer this flow converges. Questions you might want to ask: does this converge? Well, optimum. If yes, which one? And in what time? An example is small neural networks. This is the most baby example of a neural network. And I have perhaps some loss at 0, yi, and then f of xi and theta plus lambda square, and then here f is perhaps something like this. And here the parameter theta is theta 1. Okay, so it's a matrix K by n, and our results by this, sorry. And our results cover the case in which K is fixed and the dimension goes to infinity. Okay, and here, of course, we might want to understand same questions given a certain D and N and random data. Does this gradient descent converge, gradient flow converge? So, of course, gradient flow is defined in the same way as here. Does gradient flow converges to the global optimum? Which one in what time? Okay, and sharp answers to these questions are not known even in very simple example. For instance, one example that we studied recently is the negative perceptron. Example that at least I would like to understand, and in that case we have ln of theta is let's say yi this case, this L has this form. This hinge is 0 for argument bigger than kappa and 0 otherwise. And so this is one specific, very simple example in which I don't know the answers to these 3 questions. Okay. Any question about these examples? Because now I'm gonna introduce a setting of which these are special cases. And so the setting is the following general flow. So we have a matrix. So all of these have the property that depends on a random matrix. And this will be the matrix of the data. Yeah.
So you think linear perceptron is an example of GLM, right?
Yeah, in this exception of in this definition of GLM that doesn't include, of course, it's more general than what in statistics are general.
Sure, but so in that case, you think we need to map explicitly? I'm a bit confused by
the normalization of theta. Oh, okay. Here perhaps I can put square root of t. Let's see. My normalization, I'll put this, and here this is a special case, right? L0, if I call this, so this is my function. Let me give a different name, because b of t.
Okay.
Okay, so this fits where L0 of z y is just b of yz.
So, but what's the here? I mean, phi here is defines. So the z
Phi defines the labels, right?
So the labels here. I mean, look at this. In this lesson, I mean, 0 is a global optimum, right? Or
No, 0 is not a global optimum because I'm imposing this constraint.
But over there, you're not constraining.
Well, yeah, okay. I'm not constraining in reality. Okay, we can constrain this, but we can put lambda negative and basically constrain that.
Okay,
here lambda doesn't need to be
also
positive.
here
Yeah, so there is a little bit to fit exactly the strong constraint, the hard constraint, one has to fiddle a little bit around. But yeah, we can think of also of the following: maximize.
So this should, I guess, it's lambda being negative.
Yeah, lambda doesn't need to be positive. Yeah. Any other question? So this negative perceptron is basically the problem of you have a polytope that contains the origin, and you want to find the vector with the maximum L2 norm in that polytope. All right. Okay, so okay, all of these have the property that are flows that depends on a matrix, on a random matrix that is n by d, and okay, on a vector z that is an Rn, and then I will have a sequence of functions that are Rk times Rk for each t bigger than 0, and then a sequence of matrices lambda t that are Rk times k, and then the flow acts on vectors that are d by k. And the way it acts is in the following way: d theta t in dt is equal to minus theta t lambda t. Okay, so this is a matrix. This is minus d over n x transpose lt x theta t z. Okay, and this is the convention is that this is applied entry wise, right? So lt of x theta z component I is just lt of xi theta that's really xi transpose times theta, and that's that. Okay, so the previous should be clear that there are special cases of this. For instance, the first case can be embedded in this by taking, in fact, k equal to 1 has to take. Okay, now assumptions. Let me write assumptions for the theorem. Notice that this is more general in that lambda can depend on time. This doesn't need to be a gradient, and this depends on time. Okay, and the assumptions that we're going to make are the following. So the matrix Xij has, okay, there is this scaling. That is just to have a nice normalization, and then this will be IID with mean 0 and variance 1 and order 1 sub-Gaussian, and then okay, some regularity on this coefficient lambda t, Lipschitz bounded, and t differentiable with d t. So this, the whole map t. Write it explicitly. T w z to L T w z differentiable with d T w z, so with the Jacobian Lipschitz bounded. Okay, and then finally we look at the proportional asymptotics n d to infinity with n over d that. Okay, so of course, each of these assumptions excludes some interesting cases, but so now I can state the theorem. And the theorem is like this. Okay, so I state it in a simple to understand form. So for any integer m and any times t1 tm, and any function psi r k the m times r tilde r k r times r. The following happens. So I look at 1 over d sum over y1 to d of psi theta I t1 theta I tm limit and d to infinity, in that proportional asymptotics. So what are we looking at here? I'm looking at, I take one coordinate, one row of this matrix. This matrix is evolving over time. So I look at the empirical, basically the empirical distribution of the coordinates, okay, at multiple subsequent time. Think, for instance, of the case k equal 1. So I look at coordinate 1 at time t1, at time t2. This, has some trajectory at time t3, etc. And I look at the joint distribution of that m times. And then I compute the limit of this, and I claim that this limit exists. And okay, I'll describe the limit in a minute, but this is given by a certain stochastic process that I call psi here. And a similar thing happens for the residuals. Okay, if you have a theta star, and the same for residuals. Okay, and now, so the limit, I'll describe it in a minute, where psi t. So this is a stochastic process, and RT is another stochastic process, and these are what we call the dynamical mean field theory process. But okay, before defining the limit, I want to just, clarify or make sure that it's clear what is this theorem talking about. I look at, again, there is this whole vector that evolves in, a very large dimension. This is this vector theta. I take one component I. Each component has its own evolution over time. Each entry has its own evolution over time. I take one of these component I, and I look at snapshots at m different times. And the claim is that the joint distribution of these coordinates converges to a limit that I can characterize. And the same happens for the residual. So a special case, this allows you to compute things like the estimation error after time t. This is simply taking psi the square function. Now I should say that this is actually bounded Lipschitz in a way. But okay, let's say that you threshold that, and yeah, well, or you can compute stuff like this 1 over n.
T doesn't depend on I, right? It just takes.
Yeah, psi doesn't depend on I, it's fixed.
All right, so how can you?
But yeah, I can put theta star I.
So that's I, right? But how can you do the second one?
Well, I can put here theta x theta
use
star.
the second form. Okay.
Can always put theta star as a special coordinate. Yeah, sorry. I'll find that, sorry. Okay, so very much as in the case of empirical risk minimizers with convex losses, for instance, Gaussian comparison inequality allows me to compute this kind of object by solving a set of nonlinear equations, and we have, several dozens of examples of that calculation. This allows you to tell something about, gradient descent, and okay, so we moved the kind of beyond this thing, and we are trying. Now, any question about this statement? Yeah.
I have a question about the so where like key so the so theta you have k thetas.
Yeah, so yeah, you have k theta. So I'm thinking of theta as a matrix d by k, right? And theta I, okay, so it's really the ith row of this, okay? So now you're right, because when I explained this example, I called, when I explained the neural network example, I called theta i's the columns of this, and how I'm calling theta i's the rows of this matrix, right? So this is a very skinny matrix. And what, constant number of columns and diverging number of rows. In the neural network example, this corresponds to a constant number of neurons. And I'm looking at the empirical distribution of the rows. And so this is telling you that basically the empirical distribution of the rows, finite dimensional marginals at, many times at constant number of times converges to a yeah, so the second one is this case, right? So we have not only the process of thetas, but process also of x times theta. Yeah. So this is x theta t1 component I. So I take the matrix theta, I multiply that by x. Now this is what? This is a matrix that is n by k. Okay. And I'm looking at, again, the rows of this. Yeah. So think of k equal 1 if you want. That is and all the others are basically. Any other question? I realize that this is perhaps not. Yeah.
So you're taking here n and b variance, so x. So what you what are you assuming here for x?
Oh, what I'm assuming here for x is this statement, right?
Oh,
okay.
Okay.
That x has IID entries, basically. Okay, the scaling is whatever you need to make things be okay, and then it has IID entries centered and order 1 sub-Gaussian. Now, okay, natural question is, can you generalize this to some other nice matrix model, introducing some correlation? I think so, but okay, this is the theorem. So far, this is the theorem. And so, yeah.
Are you going to tell us what the Kasai are?
Right, yeah, so I'm gonna tell you the next question, but before I wanted to make sure that things let's make sense here. Because, so basically, again, this is taking one coordinate of my large vector, looking at the process that this coordinate follows, and claiming that the process that is coordinate or the process of a specific residual converges to a limit, and we have a characterization of the limit. There exists a characterization of the limit. Okay, so the characterization, before giving the characterization, let me I want to give you some summary of what's nice and what's not nice about the characterization, so that you don't have to understand the characterization to have an idea of what can do for you. So this name, first of all, comes from physics, of course. And I'll give you a few references. This is kind of a by now classical topic in physics. Okay, one nice thing is that this psi and this r are defined are stochastic processes. In order 1 dimensions. Okay. So we started with a very high dimensional process, and now we reduced it, for instance, in the case of the GLM, to a 1-dimensional stochastic process. They are stochastic processes that they are have no random coefficients. If you think about it, we started with something like this that has some random axis, and I'll give you stochastic processes for psi and r that are stochastic, but the coefficients are not random. And so these are two nice things. One not nice thing is that these processes are non-Markovian. And okay, I don't know if good or bad, but okay, they are parameterized by 5 functions that are called C theta. So this is functions of 2 times. Theta is a function of 2 times. CL is a function of 2 times. RL is a function of 2 times. Gamma T is a function of 1 time. And again, as I said before, describe the dynamics single row. Okay, so perhaps I can tell you one word about why you should expect that this is non-Markovian, is because if I focus on a single coordinate of this, vector, of this very large vector, say the first coordinate, this will have some impact on the other coordinates at some subsequent time. And this later on will have back impact on the first coordinate, right? So if you start a Markov process and you take a low-dimensional projection of a Markov process, you get a non-Markov process. The nice fact is that the non-Markov process that we obtain, that one obtains is quite, it's not general, but it's quite specific one. Now I can write it down. So the process that you obtain is the following. So the process for psi is actually Gaussian in this case. can write it down and then I'll explain it. Okay, so let me explain you. So what is the deal here? So as I said, the process is parameterized by this 5 deterministic function. This is a function of 2 times, function of 2 times, etc. I'm thinking of k equal 1 for simplicity, but in reality, these are matrix value functions. Okay, and what happens? So you give me this 5 function. I generate noise that has covariance CL divided by delta. Delta is n over p. Okay, and then now I integrate this stochastic differential equation. This is a linear stochastic differential equation with a memory. Yeah. Sorry. Sorry. Yeah. Thank you. Okay. So you generate this Gaussian process with covariance CL, and then you integrate this. This is a linear differential equation. It's stochastic in the sense that the noise is stochastic, but otherwise it's completely trivial. And then this gives you process psi. And the claim is that the coordinates of this original gradient flow, or whatever flow you want, converge to this psi. And gamma is also one parameter of the process. And now now I'll tell you. So an interesting fact is that the regularization term gets added this extra term, and then you have a memory, right? So you have, this is non-Markovian for 2 reasons. First of all, the noise is not Brownian motion; it's not white noise, and second, there is this memory term. Okay, and the same fact for similar thing for the response here. You generate W with the Gaussian process C theta. You plug it in here, and then you integrate. You solve this integral equation. Now this integral equation is nonlinear, so the process R is not a Gaussian process. The process Xi is a Gaussian process, and the process R is not a Gaussian process. Now, how do you find these 5 functions? So any question about this? So this defines completely the process, or completely defines the limit of this gradient flow, this proportional asymptotics, if I give you these 5 functions.
I don't understand why psi is Gaussian, because gamma is not Gaussian.
This is deterministic, right? So this is gamma is
lambda, sorry.
Yeah, this is a determinant. So I'm deriving my
sorry. Gamma, I didn't gamma. So
gamma. So all of these functions. So this function is deterministic.
Wait, is this gamma or R in the second equation?
Sorry. This is a gamma, capital
This is
gamma.
gamma, and the second one.
And the second is R.
Oh, okay.
Sorry.
So these are completely separate.
Yeah, so these are
okay.
completely separate,
Okay,
as it
sorry,
should be, because one is the residuals and the other is the parameters, and they live in different dimensions. So they basically live in different worlds.
That C over there is the noise from the original dot, or is it
This what this? Yeah, so this Z is the same noise here, right? So now there is a little gymnastic because here I brought the loss in terms of Y, not in terms of the noise. So you have to substitute this here, plug in there, and then do the gymnastics of the change of variables.
What lambda with the general generalization? What's
Yeah.
gamma?
So gamma is a function that, as any of these 5 functions, I have still to tell you how to find. So, okay, so how do I find these functions? This is C. So this they are a solution of 5 equations. These are fixed point equation. So C theta is the covariance of S transpose CL yes and C transpose R theta yes is the excited the yes RTZ the yes gamma T is the expectation of the gradient with respect to R of n. What is the deal? So the way I think about this as a fixed point equation, start with some value for this function, some guess for this function, R, RL, R theta, CL, C theta, and gamma. Solve this stochastic differential equation, compute this expectation, or simulate this stochastic differential equation, compute this expectation, and solve it. Okay, so this is, of course, so the question of studying this equation is future work. But as we saw this morning, mean field theory 3 years ago was we had very few applications. Now we have a lot of them, or few of them, and hopefully the same will happen with this. No. So okay, part of the proof is that this iteration that I just described is a contraction, so the solution exists and is a contraction in a certain space, so the solution exists and is in it. It should be. One thing that we prove, okay, so one thing that we can prove is that, so I started with this analogy with Gaussian minimax theorem, and okay, let me state informally theorem. You can look for solutions of these that are stationary, that depend on time, non-depend on time. Basically, they are fixed points. So stationary solutions, the system of equations are in correspondence with stationary points of the Gaussian minimax theorem, the Gordon inequality. Any of if you take, if you look at the case in which we are minimizing, for instance, this loss function, there is a lower bound on the loss. That is the kind of thing that Freddy was doing yesterday. That is Gaussian minimax theorem, and this gives you a variational principle, and these fixed points corresponds to time-independent solutions of this. Okay. So one nice thing about this old theory is that allows you to talk about cases that are over-parameterized and in which you look several times at the same data. So okay, I don't know, I don't have a lot of time, but I want to say a couple of more things. First thing about the history of this subject. So the subject, this type of equation were first written in physics for spring glasses, starting with Linsky. 1981. This was for the SK model. And since then, there are hundreds of papers in physics that studies this kind of things. Quite a few, Crisanti Sommers, Gugliandolo Curcian, and many others. And recently, people like Giulio Biroli and Lenka and Florent have used this type of equation for ML stats problem. So these kinds of give some rigorous theory for that kind of applications. So they showed that in some cases you can study these equations. In math, there is also a history that is a bit more recent. Benarus proved this kind of equation for the SK model in 1996, and with Dembo, Patrick model with Dembo in 2006 for the spherical spin glass. And all of these are based on technique that use in a crucial way the fact that the matrix X is Gaussian. So this is based on a large deviation principle, and this is based on weak convergence and Gersonov formula. And very recently, work on non-Gaussian matrices has been very recent. There is a paper by, again, Amir, Eyal Lubetsky, and Ofer Zaitouni. It looks, so 2000, I think it's 20, looks at asymmetric SK. And there is a paper by Dembo Gesari. That looks at some system interacting diffusions, so it's a bit different. This is very so this is for non-Gaussian. Work on non-Gaussian is relatively sparser, and so this is regarding the history of the subject, and perhaps one word about proofs. And then I stop here. What about proof? So the proof is very different from what these people do. We use a really pedestrian approach. We discretize the flow. So we introduce a step size eta. So if you are starting with the gradient descent, so we really look at gradient flow. We look really gradient descent with step size eta, and then we show that so this is something that even before the discrete flow. So discrete flow or discrete gradient descent is equal to an approximate message passing algorithm plus post-processing. So this is a class of algorithms that have some particularly convenient property, and there are first order methods. And if you apply some post-processes to the rows of theta, you get discrete gradient descent. And then use for these algorithms, we have a lot of results. I've been working on this for several years. Use existing results. And in particular, for this, there is a universality result that we can leverage. So we leverage, there is one with Moss and Bayati and Marc Lelarche, and there is one that we actually use with by Wei Ko Chen and Lam. It is also very recent. And then, okay, basically all the work is in to show that you can take the limit of step size to 0. Basically, the step size doesn't matter. Okay. Let me finish with a couple of questions that I think, for future study. Question 1 is, okay, so would be interesting to look at X with correlated columns. I think that something can be done, especially if you have this simple range regularization. So for instance, xi normal 0 sigma, I think that there is something that can be done in this case. And question number 2, derive some concrete consequences. One case that we can do is the baby case is linear regression. Okay, how do I want to write it? Theta t, d theta t dt, x transpose y minus x, theta t. This is just gradient flow with respect to square loss in linear regression. This we can, analyze with this technology. Not that exciting because this you can do it also by linear algebra plus random matrix theory if you know how to compute certain integrals of the Marchenko-Pastur law, but still it's nice to see that we can recover those cases. Probably in the next interesting case is to do either small neural networks or negative perceptrons. Okay, I guess I'll stop here. Yeah.
So, what kind of, I mean, I'm trying to understand applications of so what kind of question about, say, fuller neural network or
Okay, so
non-convex linear model do you expect to do?
okay, so this is one thing. This is one example. Okay, let me give you the example. This is not a particular, admittedly not a particularly exciting example from an application perspective, but I think it's just for take again this negative perceptron. So you want to, let's state it in this way. For all I. Okay. And let's say that we take our, let's say, yi xi for plus minus 1 times normal 0. Right? Now, we have a characterization of what is, so n over d equal delta, and we know that opt of this problem converges to a certain, a large, I don't remember. Large delta behaves like something like this. So we know the value of opt of this problem, right? So we know that if you, cut this in this way and we start of 0, we know the value of opt. Yeah, on delta, right? So okay, here I should be precise. we scale things in the right way, we know the value of opt. We know also that there exists an algorithm that achieves some other value that is strictly less than that. And now, so if you do simulations with this algorithm, there is a linear programming algorithm. So this you try to achieve some radius r. This algorithm has a nice threshold, and this is lin. Now, if you run the gradient descent, we observe that in this specific algorithm, in this specific problem, we observe that gradient descent achieves a strictly larger radio than this linear programming method. And so the question is, okay, so just to make the story short, is what is the value on this problem that is achieved by gradient descent? And one way to run gradient descent is simply run gradient descent with respect to minus theta square plus sum over I, some barrier function of yi xi theta. I say if I want to make it smooth, I put some barrier function here at the inequality, and then I run gradient descent with respect to this non-convex thing. And then I want to see what point it reaches. Once I see which point it reaches, I can also try to understand perhaps the risk. So this is one case that I understand, at some level relatively well. Now we can try to answer the same question for ideally for neural networks with a constant number of neurons. And I would like to understand, for which values of n over d I can achieve an interpolator. I run gradient descent, gradient flow starting a random initialization. Do I reach an interpolator? And second is, what is the test error of this interpolator?
But then you don't need, functions, you're looking at functions in multiple points, then you can separate the other one point.
Right. Yeah, so all of these questions concern one single time. Yeah. Yeah, this characterization actually multiple times is just because once you do the theory, it's natural to work with that. But, yeah, it is the right object, it's the right notion of convergence.
Additional questions? Okay, so we'll resume at 11:30.